In this beginner guide to working in R, we're going to get a taste of some basic data analysis. We're going to be building on what I started in a previous video where we imported a employee survey data file. And just to get a sense of the data we're working with, let's load up that data frame. So we've got about 1,500 observations. For each observation, we have an employee ID, a rating for satisfaction level, a rating for their last evaluation, how many projects they've worked on, the average monthly hours they work, etc. You can skim through the columns to get a sense of what information we have to work with. And this information is just a demo data set that was created. If you want to follow along in this video with the data set, if you go to the notes that accompany this video, I have some code that you can paste in that's going to pull in the data set from a public URL that I've set up. And then it's going to do the processing on the data that I covered in the video that came before this one. There's also a link to the video there. Basically, the cleanup we did is we identified there were two categorical variables within the data for department and salary. And so we converted them to factors. And then the other thing we identified was there was a bunch of missing rows, so we went ahead and omitted them. So that sets us up to accomplish the goals we have in this video, which is to do some exploratory analysis to better understand the data. And this is going to entail generating basic descriptive statistics and visualizations, identifying outliers, and finally, looking for any correlations amongst our variables. All right, so we're going to get to know the data, and along the way, we're going to learn about all the tools that R provides to accomplish these tasks. So with our end goal in mind, let's get started. In the previous video, I started with a script called o1-process.r, and so I'm going to create a second script now called o2-analyze.r. And this is just going to allow me to divide and conquer. So in the process script, I worked on importing my data and cleaning it up. And then let's go ahead and make sure we've sourced all of this code. So we've got our employee survey data frame ready to work with. And now in Analyze, we're going to write the code to analyze this data. And the first thing we want to do is just get some basic summary statistics to get a general sense of the data we're working with. The quickest way to do this using base R functionality is just to use the summary function. So we're going to pass it our employee survey data frame. And you can see that gives us pretty decent output for each of our columns. We could see what the min and max values are, mean, median, the different percentiles. But let's get a better insight to this. I want to pull in another package that's just going to give us a more sophisticated summary. And the package I want to pull in is called skimr. Skimr is not officially part of the tidyverse library of packages, but it uses a lot of tidyverse conventions. So we're going to use piping to pass our employee survey to skimr. So let's first reference employee survey, and then we'll use the tidyverse piping characters and pipe that data to a function called skim that comes from the skimr library. And just to streamline our output, I think it makes sense to exclude the employee ID column. We don't need to see summary statistics for that because it's just a numerical identifier for each employee. So let's filter that out. And to do this, we're going to use the dplyr package from tidyverse. This is going to give us some basic data manipulation functionality, which will be useful throughout this guide. So let's make sure we've got dplyr accessible. And then from dplyr, we can use the select function. And what we want to do is we want to exclude employee ID. So we're just using the negation character here and saying don't include the employee ID column. So that's going to filter it down just to the other columns we want, and that will get passed to skim. And let's go ahead and run that. Our output is a little scrunched here. So what I'm going to do is I'm going to expand my console and just run that again. So that's much better. And as you can see, we get a lot more details from skimr than we did with base R summary, and it's just formatted a little bit nicer. It's easier to skim through. So let's go through this information starting at the top with the summary. We see we've got about 15,000 rows. We have 9 columns. For the data types for the columns, we see that we have 2 factor columns and 7 numeric columns. Group variables is indicated as none because we didn't do any grouping when we passed this data to skim. We could, if we wanted to, we could have included the group by function, and let's say we wanted to group by the salary levels. That would yield us skimr results where everything is grouped by salary, but we didn't do that, so we just see none there for group variables. What follows is more details about each of our variables. So here's information about our 2 factor variables. So that was department and salary. We see number of missing is 0 for this, and we'll see that as well for our numeric variables. And that makes sense because when we were cleaning up our data, we handled missing data. There was a whole bunch of missing data that we just omitted from our results. So as expected, we're seeing 0 for number of missing. For department, we can see that we have 10 unique levels, and here's a breakdown of the top levels as well as their counts. And there appears to be a clustering of employees in the top 3 departments. So sales, we have 4,100. Tech and support are in the 2000s range. And then IT in the fourth slot drops down to 1,200. So there's definitely a clustering happening. And in fact, to get a better sense of that, let's go ahead and do a bar chart of department just to visualize the distribution across the departments. It's always a good idea when you're getting a lay of the land with your data to visualize your categorical variables. So for this, let's go over to the notes that accompany this video and scroll down. I have some code that will generate a nice bar chart for us. So I'm just going to copy that code and let's bring that in. And we'll paste it at the end. This is using the ggplot2 library from tidyverse, so let's make sure that's included at the top. We no longer need this line where we're getting a summary of employee survey. All right, so here's the code that's going to generate our bar chart. And just a quick run through this, we are piping our employee survey data to the ggplot function. For the aesthetic, or what we want to be plotting, we're going to set X to be the department. We're looking for a bar chart, so we're going to use ggplot's geomBar function. Here are the labels we're going to add to our chart. We're going to use the minimal theme just to make things nice and tidy. And then this last line is just doing some customization so that the labels for departments are displayed at an angle so that they can fit. Let's go ahead and see what this looks like. So let me expand my plots panel. So as you can see, we've got 10 different departments, and just like we saw in the skimmer output, we can visualize here how there's a high distribution amongst the sales, support, and technical departments. Focusing back in on our skimmer results, the other factor column we had was for salary. So we can see that this was a ordered factor, and our 3 different levels were low, medium, and high. And it appears most employees are in the low or medium salary range, with the high range being a much smaller group. Once again, a picture is worth 1,000 words, so let's visualize this. Let's change our X here to salary. We'll update our title and our X label. Rerun our plot. And here we can very clearly see how most of the employees are in the low or medium bin. Moving on from our categorical variables, let's take a look at our numerical variables. So I'm just going to run that skim again. All right, so here are our 7 numerical variables. For each of these, we can see our central tendency via a mean value. We can also get a sense of the spread of our data via the standard deviation, where a smaller value means that the data points are closer to the mean. In other words, the data is tightly clustered. So things like satisfaction level, last evaluation, those are tightly clustered. Whereas a larger standard deviation tells us the data points are more spread out, there's greater variability. So we can see that in things like our average monthly hours. And then we've got our different percentiles. So P0, we see what the minimum value for the column is. And P100, we see what the maximum value is. For P50, that's our 50th percentile, so our median value. And then for P25, we've got our 25th percentile, or the first quartile. And for P75, we've got the 70th percentile, or the third quartile. And then finally, very helpfully, Skimmer provides a nice little mini histogram to get a broad sense of the distribution of our values in these variables. For an example, let's dissect the mini histogram for satisfaction level. We can see that this is left skewed with a long tail to the left, indicating we should expect to see more values in the high range than in the low range. And just like we did for our categorical variables where we created those bar charts to really visualize them, we could do the same thing with our numeric data by creating actual histograms. It's just going to give us a closer view of the data spread than we're getting from these mini histograms. So let's do that for satisfaction level. And once again, I'm going to go over to the notes for this code just to expedite things. So we're under the section numeric variables. And if we scroll down, here is the code to create a histogram for satisfaction level. So we're piping our data to the ggplot function. The aesthetics, or what we're mapping in this case, is satisfaction level. We're going to be using the geom histogram function from ggplot2 to create a histogram. Here are the labels we want. Once again, we're going to use the minimal theme to keep things tidy. And let's run that and then expand our plots panel. And you can see we get a much more nuanced view of what we saw in the little summary histogram from Skimmer. And that's just because we have more bins to deal with, so we see the data in more detail. So of course the takeaway here is use the mini histograms as a broad sense of the data, but definitely take a closer look with individual histograms. Moving on, let's continue to play around with some visualizations. Particularly, I want to create some box plots to see if we can identify any outliers in this data. In the notes, if you scroll down to the Visualize Outlier section, we can grab the first chunk of code here. And before I break down what this code is doing, let's go ahead and run it so we can see the resulting plots. So as you can see, this generates a grid for several of our variables. And just as a refresher for what a box plot tells us, the box itself is indicating the middle 50% of values, or the interquartile range. The line inside the box indicates the median value. The whiskers that extend outside the box indicate the range within 1.5 times the interquartile range. And the dots indicate any outliers or values beyond the whiskers. And looking at these plots, we can identify that time spent company is the only variable with outliers. We've got some values up here at the 6, 7, 8, and 10-year mark, suggesting there's a small group of long tenure employees at this company. So now that we've seen these plots, let's rewind to the code that created them. The first step in this code was identifying which of the variables we wanted to create box plots for. And we begin by narrowing it down to just our variables that are numeric, and also just our variables that have more than 2 distinct values. And the purpose of that is to filter out our binary variables. So looking at our data, there are 2 binary variables. One is for work accident and also promotion last 5 years. The values here are either 0 or 1, 0 indicating no, there's never been a work accident or there hasn't been a promotion in the last 5 years, and 1 indicating that yes, there was one of these 2 different things. So we don't need box plots to look for outliers for binary data, so that's why we're excluding it. And then finally, for our purposes, there's no meaningful information in the employee ID column, so we exclude that as well. So that identifies the columns that we're interested in, and then with that data, we're going to reshape it from wide format to long format using the pivot longer function. The reason we're doing that is because that is the format that's going to be expected by this facet wrap function we're going to be using from ggplot that allows us to create multiple plots in the grid like this. And just to clearly visualize what pivot longer is doing, hopping back to the notes, scrolling down, I have a screenshot of what the data looks like before and after that pivot longer function. So before, it's in wide format. So we have each of our variables in its own column, and it's got the respective values there. But once we run pivot longer on it to go to long format, we end up with a data frame where we have 2 columns, one for the variable and one for the value. And that, like I said, is the appropriate format we need to pass this information to that facet wrap. So continuing on in the code, of course, we're going to invoke ggplot, and we're going to be mapping to the x-axis our variable and to the y-axis our value. The geom we're going to be using is the boxplot geom. The facet wrap function, as I said, is going to allow us to wrap the plots into a series of panels. So this is going to create 1 plot per unique value of the variable column. And this argument scales equal free makes it so that each individual subplot or facet has its own y-axis to accommodate the different ranges of values, right? Because obviously something like average monthly hours and last evaluation, they use a very different range of values here. So we want to make sure they have their own unique scales. So box plots are a great way to quickly visually identify any outliers in our data. But let's imagine we had a lot more variables we're looking at, or we just wanted to be more precise about it. We could programmatically write some R code that would identify outliers for us. And of course, I've got an example worked up for this. So in the notes, if you go down to programmatically identify outliers, there are 2 steps that we're going to follow here. The first is to define a function called find outliers. This is what's going to actually identify the outliers in our individual columns. So let's bring that into our script. And we'll go through that in a moment, but let's also bring in the second part, which is going to apply that function and actually find those outliers. So we'll copy that and add that in. And once again, let's run this to see what the results are, and then we can talk about what the code is doing. So let me give myself a little bit more room here. Let me first load this function, and then let's go ahead and execute this section to get our outlier counts. And then let's throw in a print statement just to output the outlier counts. Run that. And here is our output. So we've got our variables of interest and a count of outliers, and this matches up with what we saw in our box plots. So the only variable with outliers was time spent company. And we can see a clearer picture of how many outliers we actually had. So the total count was 1,282. Once you've identified outliers, the next logical step is deciding whether you want to exclude them from your data. which of course is going to depend on many factors that are a bit beyond the scope of this video. So I'm not going to get into that, but I will show you how you would exclude them from your data if that's what you decide to do. In the notes, you'll find the code to remove outliers under the section aptly titled Removing Outliers. So let's copy that and bring it in to run through. Step 1, we need to extract the outlier values. So we create an object called outliers. We're going to be getting this, of course, from the employee survey. We're going to be looking at the values for time spent company. And for each of those values, we're going to pass it to our find outliers function, which we had already defined above. And just to understand the end results of this, let's go ahead and execute the code. And then let's take a look at the outliers result that we get. So this is a vector of integers for all of our outlier values. And we're going to use that in the next step to essentially filter them out from our survey data. To do that, I create a new object that will store this version of our data. If I wanted to just update the existing employee survey data frame, I could just write it like this. So this would create basically a modification in place of our data, whereas this is going to be creating a copy of it. Regardless, we're going to be working with the employee survey as our data source that we're going to be filtering. And what we're doing, we're not actually filtering out the outliers. Instead, what we are doing is we are selecting the non-outliers, right? That's what's going to give us our data without outliers. So we're looking for time spent company values that are not in our list of outliers that we identified. And the not is coming from this exclamation point here. All right, so grab all the data for rows where time spent company, its value is not in the outliers that we identified. Let's go ahead and run this, and then let's expand our environment panel so we can just compare before and after. So this is our original data employee survey. We've got about 15,000 observations, and then here's the copy we just made, employee survey without outliers, and we narrowed it down to 13,717 observations, which let's go ahead and do the math there. So we're going to say 14,999 minus 13717. So that's a difference of 1282, which makes sense because earlier when we got our outlier counts, we saw that it identified 1,282 outliers in time spent company. So far, in all of our examples, we've been focusing on individual variables, but the last example I want to take a look at is to see if there's any correlations amongst our variables. To accomplish this, we're going to use R's built-in core method. This will generate a Pearson's correlation matrix, and then we're going to visualize that using a package called corrplot. In the notes, the code for this is under the correlation section. So let's copy this and bring it into our project. This is going to be using the corrplot external package. So we have a library command we need to place, and I'll just put that at the top with my other library commands. Let's go ahead and run that, just make sure I have it installed. If you get a notice here about this package not existing on your system, you can install it just by running the install.packages command within the console. Step 1 of this code is to identify the variables we want to include in our correlation matrix. And just like before, we're going to be focusing on just our numeric variables, excluding any of our binary variables, and also excluding the employee ID. With our columns selected, they're going to then be passed to R's built-in core method. This will generate a matrix of correlation values for the columns that we selected. The use argument here is saying that we should only be looking at complete observations. In other words, exclude any observations that include NA or missing values, which in our case, we already tidied our data. We made sure we removed any missing data. So we could technically omit this, but I'm just going to leave it there for the sake of this example. All right, now before we move on to plot the correlation matrix, let's just understand or make sure we understand what this code is giving us. So I'm going to select just the part that we've reviewed so far, and let's go ahead and run that. So here are the results, and we can see where we have, for example, positive correlations, where we also have negative correlations. And we could stop there, but to make this a little bit more visually compelling, we're going to use that corrplot method from the corrplot package to generate a heat map of these values. And I have a bunch of different attributes set here just to tweak what this heat map's going to look like. So let's go ahead and run this full thing so we can look at that heat map. And here are the results. So as you can see, for each of our variables, we can see our correlation coefficients, and they are visually indicated with a circle, where the larger the circle, the stronger the correlation. The circles are also colored, so positive correlations are represented in a shade of blue, and any negative correlations are represented in a shade of red. And just like the size of the circle, the darkness of that shade is also indicative of the strength of the correlation. All of these visual characteristics of our heat map are finely tunable via the corrplot function. There's lots of different arguments you can play around with and different values. I recommend pulling up the help files for corrplot. So I'm just going to run $corrplot in the console to do that. And you can see, for example, for the method argument, I chose circle, but there's several different options that you could play around with. And like I said, there's a lot of different things that you can tune about these heat maps. So take a moment to skim through the documentation just to familiarize yourself with what's possible. And speaking of what's possible, this video has really been just the tip of the iceberg of what you can accomplish when it comes to data analysis and visualizations in R. So I hope that the examples that I have shown have given you a good sense of where to start and also some motivation moving forward.